Hey everyone, and welcome back. Today we're going to be continuing our exploration of differential calculus and discuss how to do differentiation in two different coordinate systems, in particular polar and parametric. So let's start off with polar curves, since their curves are typically a little bit more periodic, I guess you could say. So let's look at a polar curve that you probably already know the representation of. In particular, r is equal to the sine of 3 theta. And keep in mind, in the realm of polar coordinates, the independent variable, I guess you could say, is typically taken to be the theta variable. In particular, how much have you rotated around the origin, with r being the radius of a circle centered at the origin. So every time you see r, distance from the origin is typically a good interpretation of that value, and theta being how much have you rotated around that origin. So if you already know some basic polar curves, sine 3 theta is just going to be a rose curve with 3 petals. So let's assume that the domain of this particular function, theta, belongs to the interval 0 to 1 pi. That's going to give us a complete cycle of our 3-petal rose curve. So as we already know, when theta is equal to 0, sine of 3 theta is also going to be 0. So that center point is going to be the origin. So if we go through, for example, 1 pi unit, that's going to give us the first petal of that rose curve. Pi over 3 to 2 pi over 3 is going to give us that petal, and then from 2 pi over 3 to 3 pi over 3 is going to give us that particular rose petal. Obviously, this should look a little bit more symmetric, in particular that, right? So for example, if we were to draw some little lines here, tailing out to the tips of these petals, you pretty much get this type of curve, where the angle between each of these dotted axes are just 360 divided by 3, so 120 degrees. So this is going to be our curve. So what we're going to be interested in studying is how is the distance changing with respect to a slight change in theta, right? Because we're trying to extend our interpretation to the calculus of polar curves, right? So the derivative with respect to theta of our function of theta is going to be equal to what? So if we just use the definition of a derivative, just like we did in Cartesian coordinates, that's just going to be equal to the limit as epsilon goes to 0 of our function f evaluated at theta plus epsilon minus f of theta all divided by epsilon, right? So that would be the definition that we're going to still use in the polar coordinate realm. But keep in mind, in the Cartesian realm, this was usually interpreted as the tangent line of a curve, or the line, or the slope of a tangent line to a curve at a particular point. But in polar curves, the derivative has a subtly different representation, right? So how would we interpret this? So how much would or does our r change with a small change, typically taken to be positive since we're usually approaching 0 from the right hand side, in our parameter theta, right? So if we look at a particular phase of our polar curve, and keep in mind the direction for which this curve traverses also matters a lot, especially when interpreting derivatives. So if we look at a particular petal of this rose curve, for example 0 to pi over 3, so that's going to be equal to this curve. So what we're going to do is we're going to pick a particular angle theta, right? So let's choose like theta is equal to pi divided by 30 or something like that. So if we choose some angle theta, right? So theta is going to be this angle here. What is the distance of that curve to the origin, right? So this distance here from the 0 to that point, that is f of theta. So let's assume we go a little bit more into the future of theta, in particular theta plus epsilon. So if we slightly increase our theta, for example, let's assume that this is theta plus epsilon, and let's sort of draw the tangent line through that point. So that's going to give us that. So this distance here is going to give you f of theta plus epsilon. So f of theta plus epsilon, right? So obviously we're a little bit more farther from the origin than we were at theta is equal to whatever theta value you have, right? Because keep in mind that this particular f of theta value is associated to a particular radius or a circular radius, and this value here is associated to a more wider circle, right? And obviously the inner blue circle has a smaller radius than the outer blue circle, and hence f of theta plus epsilon is larger than f of theta, right? So if I consider the particular point right here, right, because obviously this graph is exaggerating that change in theta, but the derivative of our function f theta at this particular point, let's call it theta naught, so that theta is equal to theta naught, is positive, right? Because if you slightly increase our value of theta, that's going to put us at this point here, which is slightly farther in terms of distance from the origin, right? But if we go, say, on the other side of the circle, right? For example, that's going to give us one value of theta, and if we go slightly farther into the future, notice that we're getting closer and closer to the origin at that particular point, right? So if I were to analyze the derivative of f with respect to theta here, the derivative of f with respect to theta, at this particular point, we can call it, say, theta is equal to theta 1. So let's assume that this is equal to theta 1. That's going to be a negative number because as we are traversing along that petal of that rose, we're getting closer and closer to the origin as my theta subtly increases. So that's pretty much what we are doing here for derivatives in the polar coordinate system. We're pretty much changing as we rotate counterclockwise, how is our distance from the origin changing? So let's just look at a couple values, at least evaluating derivatives in the polar coordinate system. And let's, of course, take our three-petal rose curve as we have up to this particular point. So let's sort of graph our little rose, right? So we have petal number 1, petal number 2, and petal number 3, and those points should be crossing each other. Right? So again, I'm going to be taking the domain of this function to be equal to 0 to pi, and let's put an open interval on that right boundary. So if I differentiate with respect to theta, f prime of theta, as we already know, is just going to be equal to 3 times the cosine of 3 theta via the chain rule. Okay, so what we want to do is sort of verify that our intuition for derivatives in the polar coordinate system are indeed valid. So what do we exactly have? So keep in mind, we're going to start at 0 here when theta is equal to 0. So this point corresponds to theta is equal to 0. And we're going to be traversing along this curve. And then we're going to eventually get back to this particular origin at theta is equal to pi divided by 3, which means that we're going to be reaching the tip of that first petal when theta is equal to pi divided by 6. So if we pick a point, say, on the first sweep of the right-hand side of the petal, I guess you could say, we can pick a point, say, theta is equal to pi over 12, and see if the derivative of f with respect to theta is increasing or decreasing at that point. We've already sort of graphically convinced ourselves that it's getting farther and farther away, but let's just make sure that that is indeed the case. So f prime of 0 is going to be equal to what? So that's going to be equal to 3 times the cosine of 3 times 0, which is just 3 times the cosine of 0, which is 3 times 1, which is just going to be equal to 3. So when theta is equal to 0, my df theta is a positive number, which means when theta is equal to 0, we're going to be moving farther and farther away if you step a little bit farther into the future of our theta, which indeed we do. So if we look at pi over 12 in particular, so f prime of pi over 12, So that's going to be equal to 3 times the cosine of 3 times pi over 12, and 3 times pi over 12 is going to cancel, so you're going to have 3 times the cosine of pi over 4. That's just going to be equal to 3 square root of 2 over 2, which is again positive. So at that particular point of pi over 12, we're going to be moving farther and farther away. Now, what happens when theta is equal to pi over 6? So if we look at f prime of pi over 6, that's going to be equal to 3 times the cosine of 3 times pi over 6, which is going to be 3 times the cosine of pi over 2, or 90 degrees. And we know that's going to be 3 times 0, which is equal to 0. So at that particular point, we're not moving farther away nor closer to that origin point. So I guess you could call this particular point a turning point for that particular point that's traversing along that polar curve, right? Because before pi over 6, we're getting farther and farther away, and at least intuitionally, we can guess that slightly after pi over 6, such as, 3 pi over 12, that would be the point, say, right there. You can verify that that's actually going to be moving closer and closer. So let's actually just do a quick verification of that. So 3 pi over 12, that's on the other side of our first petal. That's just going to be equal to 3 times the cosine of 3 times 3 pi over 12, right? And what's 3 times 3 pi over 12? So that's just 9 pi over 12, which is just 3 pi over 4. So the cosine of 3 pi over 4. So that's just the 45-degree angle in quadrant 2. Therefore, that's just going to be equal to negative 3 square root of 2 over 2, which is a negative number. So that means we're not moving farther away from the origin, we're moving closer to the origin, right? And that, of course, agrees with our intuition, right? So when we plug in pi over 3, which is where we are at the particular origin, so f prime of pi over 3, what are we going to get? So that's just going to be 3 times the cosine of 3 times pi over 3, which is just going to be the cosine of pi, which is negative 1, so that's going to be equal to minus 3. So what does minus 3 mean? So minus 3 typically would mean that we're moving closer and closer to the origin, right? But if we move slightly outwards instantaneously, we're going to be moving farther and farther, and then eventually closer and closer, and then farther and farther, and then closer and closer, and that this is going to repeat every pi units. So that practically matches our intuition in terms of what the derivatives of functions of theta represent. And in some sense, what this represents is sort of how fast that position is changing with respect to theta, so you can also view it as a polar velocity in some sense. Parametric coordinates are also another nice way of representing location in the xy Cartesian plane if you happen to be working with some particle or object that's moving in a non-functional way. And when I say a non-functional way, I usually mean for a particular value in the domain, there's a unique particular value in the range that corresponds to it, i.e. the vertical line test satisfies. So let's just give a quick graph of a particle that's moving in some completely different pattern. So let's assume that we're sort of chilling at this point at time t is equal to 0, and then we're sort of traversing through this particular plane in this particular way, right? And let's assume that we eventually get back to where we were. So let's assume that this point is point A. Let's assume that this is point B. Let's assume that this point is point C. Let's assume that's point D, point E, point F. Let's choose that as G, H, I, J. And we can choose several other points on this graph to analyze if you want. So let's create a nice little table to sort of summarize what we're going to be looking at. So we have a bunch of points, in particular A, B, C, D, E, F, G, H, I, and J. And we're going to be analyzing the derivative of x and also y with respect to t. Because keep in mind, in the parametric world, our x values with respect to time are going to be represented by some function f, which usually isn't going to have a nice representation usually. And y of t is going to be represented by some other function, say g of t, let's assume. Let's assume they're well defined, or at least approximated to some numerical accuracy. So, how is x changing with respect to time? How's y changing with respect to time? So that's what we're going to be looking at from the calculus perspective for parametric functions. So parametric curves are encapsulated by two functions, f of t and g of t. So let's look at the point A. So how is x changing with respect to time at point A? So are we moving to the left or to the right when t is equal to something? For example, t could be equal to 1 at that point. So when t is equal to 1, we're moving to the right, so the x values are increasing. So we can say the derivative of x with respect to time at point A is a positive number. And what about our y values? Are we moving up or are we moving down at point A? And obviously we're moving upwards since the y values at this particular point t is equal to 0 and t is equal to 1, they are definitely moving up. So the derivative with respect to time of y is going to be positive at that point. Now, once we reach point B, notice that we're not moving to the right anymore. So the derivative of x with respect to time, or t, at this point is going to be equal to 0, but we're still moving in the upwards direction. Therefore, dy dt will be positive at this particular point. Keep in mind, as we traverse along this curve, we're still moving upwards, and I'm not sure why that looks like a C. It should look like a D, right? So there's our E there. So notice that we're still moving up in the vertical direction, because if we look at point C and some points slightly above it, we are still moving up, but we are moving leftwards in that particular direction, right? So dx dt is going to be negative, but dy dt is still going to be positive until we get up to this point D, because notice that we're not moving up or moving down at this particular point, so dy dt at that point will be equal to 0, but notice that we are still moving leftwards at D, therefore that's still going to be equal to a negative number. So including E, we're still moving to the left, so that's still going to be negative. And notice that we're going down that hill, so the dy dt will also be negative. And then we're just going to continue marching along this curve, and then we're going to be coming around that particular corner. So notice that at that particular point, dy dt is still going to be equal to a negative number. Now notice that some points here between E and F, dy dt is positive, so it's not always negative between E and F. But at F, notice that we're starting to go downhill, and also dx dt, possibly some point slightly after F, it's equal to 0, but at that particular point, it's subtly negative. And at these particular points, particular along this particular region, notice that we're moving to the right, so dx dt will be positive. We're moving down, so dy dt will be negative. At that point G, let's assume that's on that particular extreme point. Dx dt would be equal to 0. Dy dt would be a negative number. At H, we're moving to the left, so dx dt would be negative. Dy dt would be negative since we're moving down. Here, once we reach to I, now we're moving to the right, so dx dt will be positive. We're still moving down, so dy dt will be negative. And once we reach this point H or J, we're moving to the right, so dx dt will be positive. And dy dt, it looks almost flat, I guess you could say, but subtly it's still a little bit moving down. Right, so that's how we're going to be approximating or interpreting the derivatives of our parametric functions f of t and g of t with respect to our parameter time. So how are we going to define derivatives of our parametric functions? We're going to do it in a similar way. So dx dt will be equal to the limit as epsilon x goes to 0 of f of t plus epsilon x minus f of t all over epsilon x. And if you're curious why I'm using epsilon x, notice that we don't have to necessarily move in the For a subtle change in x, the change in y could be subtly different. Yes, you could consider both to be epsilon in their own individual rights, but at the same exact time, the change in x and the change in y could slightly vary, but both need to be arbitrarily small, right? We're still approaching zero for both of them, but they should be used in terms of different notations. And similarly for y, dy dt will be defined to be equal to the limit as epsilon y goes to 0 of g of t plus epsilon y minus g of t all over epsilon y. And that's how we're going to be defining the derivatives of our x function and our y function for parametrically defined functions, or curves, I guess you could say. Let's assume that we have this basic parametric curve that we want to analyze using single variable calculus, where x of t is 3t minus 5 and y of t is equal to minus 2t plus 7. So if you know anything about basic parametric curves, you probably can already identify this, since we're on a closed and bounded domain, that this is just a line segment with two endpoints. So where exactly are these two endpoints going to be located? So when t is equal to 0, notice that x, y, I guess we can just call it a point. So xy is going to be equal to just those t or xt intercepts minus 5 and 7. And when t is equal to the other extreme of our parameter values, xy is going to be equal to, so that's going to be 3 times 4, which is 12, minus 5 is 7. And then we're going to have negative 2 times 4, which is minus 8, plus 1 is going to be minus 1. So we're going from minus 5, 7, so that's our initial point, and then we have 7 minus 1, that's going to be our terminal point. So what we're going to have in the xy realm is going to be our initial point over here when t is equal to 0, and our terminal point over here, which occurs when t is equal to 4. And then this is going to be a line segment. You can choose some points if you're not comfortable with jumping up into that, traversed in the downwards direction. Right, so that is our curve, which is obviously a line segment. Right, so if we sort of analyze this just like we did before, we're definitely moving to the right at all points in the domain, and you should be able to verify that dx dt is going to be equal to the derivative with respect to time of 3t minus 5, which we know to be equal to 3, which is a positive number, right? So we're always moving right throughout the entire parameter domain. And what about our y values? So if we look at this, notice that we're always moving down in terms of y, so the derivative of y with respect to our parameter should always be negative, and we can easily verify that, because dy dt is just going to be equal to the derivative with respect to time of minus 2t plus 7, which we know to be equal to minus 2, which is always negative for all t. So our intuition definitely works. Now, obviously it is a line segment. Is it possible that we can get the equation of this line from the parametric function representation? So if we know that dx dt is equal to 3 and dy dt is equal to minus 2, what is dy dx, which we usually interpret as the slope of that tangent line, and the tangent line to a curve that is a line is in some sense the line itself. So via the chain rule, dy over dx should just be equal to dy over dt divided by dx over dt, because in some algebraic sense these dt's do cancel if you interpret these as fractions, which some people aren't exactly happy with in terms of interpretation. But nonetheless, by chain rule, this still is valid. So dy dt is equal to minus 2, and dx dt is equal to 3. So dy dx at all points time, because keep in mind, dy dx is a function of time, not x, not y, at least not necessarily, right? So it is equal to minus 2 over 3 for all time t, at least for all time t within our domain, which means as you slightly move to the right, we will also be moving downwards, right? Which is the original Cartesian interpretation of our line. So what exactly is our function of x representation? So keep in mind our function of x usually has the form y equals mx plus b, right? So we already know what our m is. That's going to be equal to our negative 2/3, and we just need to figure out what that vertical intercept is going to be. If my sketch is right, it definitely should be a positive number if this is valid. So how are we going to find our vertical intercept from a parametric form? So keep in mind our vertical intercept, which is the point 0 comma b, exists when x is equal to 0, right? And let's go back to our parametric function. When is x equal to 0? Well, x of t is equal to 3t minus 5 for all t, and we want to know when this is equal to 0. So at what time t is this equal to 0? Well, at time t is equal to 5/3. So when t is equal to 5/3, what is the y value at that point? Because that's going to be our intercept. So that means b is just going to be equal to y of 5/3, which is the point for which x is equal to 0. So y of 4/3 is just going to be equal to, so we can just plug that into our y equation, so minus 2 times 5/3 plus 7. And once we do some fraction math, we're just going to realize that that's equal to 11/3. Right? So that's going to be our b. So therefore, if we want to represent this as a function of x, then you're just going to have minus 2/3 x plus 11/3. And in particular, the domain is not all real numbers because our time parameter doesn't go throughout minus infinity to infinity, but just analyzing the x values, we've already generalized this because the domain is equal to minus 5 to 7, because since we're always moving to the right, it's never going to go backwards. Since the minimum value is minus 5 and maximum value is 7, that will be the domain of this function of x. And similarly, you can write this as a function of y as a linear function if you want to. In particular, let's call it another function. Technically, you should be using capital F since we use little f for the function of t for x. So you can say that g of t is equal to some other parameter a of y. Let's see, how would we write it? I think g of y is equal to a of y plus b would be a nice exercise to find also. So in this case, that would be the x-intercept, and that would be dx over dy. So I'll leave it to you as an exercise to figure out what a and b would be if you want that particular relation representation. Let's look at another example of a parametric function that cannot at least easily be represented as a univariate function of x nor y. And that's 3 cosine t for x and 2 sine t for y. So if you know any basic parametric curves, you probably can quickly identify this curve as an ellipse. In particular, we know it's an ellipse because it does follow a cosine pattern for x and a sine pattern for y, so it's definitely potentially a circle, but the x and y stretches are off. If that 3 and 3 were there, then it would be a circle, or 2, or r and r. R cosine theta, r sine theta would be your circle, but now we have r x cosine, r y sine, and if r x and r y are not equal to each other, that would be our ellipse. So we're starting at 2, so we know where that is. That's going to be located on the right positive x-axis, and then we're going to be rotating in this particular direction, and that's going to generate our ellipse. In particular, we're going to be rotating counterclockwise, based upon our definitions of cosine and sine. And then for t is equal to pi, that's going to be over here. T is equal to pi over 2 over here, and t is equal to 3 pi over 2 on that bottom side of our axis. In particular, in terms of distances for x and y, this point is going to be equal to 0, 2. This point here is going to be 0, minus 2. This point right here is going to be 3 and 0. And this point right here is going to be minus 3, 0, which you can easily verify by plugging in those values of t. So, how is x changing with respect to time? How is y changing with respect to time? So if I were to pick this point right here, and let's call that point A, obviously we're moving up, so dy dt would be positive, and we're moving to the left, so dx dt would be negative. So what would those expressions be? So dx dt, if we just differentiate that with respect to t, that's going to be equal to minus 3 sine of t, and dy dt will be equal to 2 cosine of t. Right? And that's going to tell you how x and y is changing at all forms t. So what if I'm interested in, for example, how is y changing with respect to x? which is different from x changing with respect to time and y changing with respect to time. So what is dy dx when t is equal to, I don't know, 3 pi over 4? Right? How's y changing with respect to x? Are we going up? Are we going down? What's going on there? So let's look at that. So dy dx will be equal to dy dt over dx dt. So that's going to be equal to what? So that's going to be equal to 2 cosine t over minus 3 sine t, which we can write as minus 2/3 cotangent of t. Right? So we can plug in any point there, get some number, and that's going to give us the interpretation. But generally speaking, if you just want to know how x is changing with respect to time and y is changing with respect to time, it's usually a lot more advantageous to keep it in dx dt and dy dt representations, unless you really have some need of switching it into the original xy system. Now, here's another question. dx dt and dy dt represent velocity, but what about acceleration? And similarly, dy dx would also be velocity, but with respect to the Cartesian coordinate representations. So obviously, if I want to find d squared x dt squared, that's just going to be the derivative with respect to time of dx dt. And if I want d squared y dt squared, that's just going to be the derivative with respect to time of dy dt. And if I want to find d squared y dx squared, that's just going to be equal to the derivative with respect to x of dy over dx, right? But dy over dx is a function of time, not x, right? So we get into a little bit of a confusing predicament here, but no worries, we can figure that out with no issue. So if we look at d squared y dx squared, which as we've already argued is the same as d over dx of dy over dx, we can multiply top and bottom of this expression by two differentials of t, because dt over tt is equal to 1, because the derivative with respect to time is equal to 1, or just t with respect to time is equal to 1. So, therefore, what we can do is we can take that differential, because dx is just a number just as much as dt is, and we can switch these dt's on the bottom with that dx. So what we're going to have is we're going to have d over dt of dy over dx and dt over dx, because they've just swapped positions. It's practically the same exact arithmetic as 1 divided by 2 times 5 over 3 is the same as 1 times 3 times 1 over 3 times 5 over 2. We're just rearranging this because everything is under multiplication. So if you look at this, this is perfectly okay, because dy over dx is a function of time and we're differentiating with respect to time. And then we have dt over dx, which doesn't really make any sense, but dx over dt does, because x is a function of time too. So if we treat this as a fraction, and there are many contexts where this is perfectly appropriate, what we're going to have is the derivative with respect to time of dy over dx, all divided by dx over dt. And that gives us an expression for d squared y over dx squared. So if we use this little derivation to our advantage to go back to our example, where dy over dx was equal to minus 2/3 cotangent of t, what would d squared y dx squared be equal to? Well, if we differentiate with respect to time, dy over dx, which is just the derivative with respect to time of minus 2/3 cotangent of t, that's just going to be equal to, well, the derivative of cotangent of t is just minus cosecant squared of t. So that's just going to turn into 2/3 cosecant squared of not x, but t, right? So that's dt over dx squared. And keep in mind, dx over dt was equal to minus 3 sine of t, which we can also write as minus 3 over cosecant of t if we really want to. So once we have the derivative of dy dx with respect to time and dx over dt, we just divide these two expressions. So once we do that, we're going to have the second derivative of y with respect to x is just going to be equal to, so we're going to have 2/3 divided by -3/1. So that's going to be equal to -2/9 times cosecant cubed of t. And that's the expression for d squared y dx squared. Now that we know how to move forward with differentiation, in particular with polar and parametric curves, let's see how we're going to move backwards in the parametric and polar world. Since polar curves only have one particular type of function, for example, if I say dr d theta is equal to the cosine of theta, all you can in some sense say about what r is just going to be equal to, okay, well, what is the derivative? The derivative of something is equal to cosine. Who is that something equal to? You can probably say that that's going to be equal to sine of theta plus some constant, right? So that much we already know just from basic differentiation principles. So polar coordinate doesn't really give us anything useful there. But what about parametrics? Now this is where the interesting thing actually happens. So we're like, okay, we know that x is changing at a constant rate of 5, and we know that y is changing at a decreasing constant rate of -7. So how exactly is x changing with respect to time, and how is y changing with respect to time? So I want to know exactly where x, y is at any particular time, not just how it's changing. So we know that x and y are functions of time. So therefore, if we just look at this particular thing and we're like, okay, the derivative of x with respect to t is equal to 5, what is x equal to each other? So we can say that x of t is just going to be equal to 5t plus some constant, let's call it c1, and y of t is going to be equal to some linear function minus 7t plus some other function c2. Right, so that's pretty easy as long as the right-hand side is just a function of t, but it doesn't necessarily have to be that way. For example, x can change with respect to how y is changing. For example, if you're going very fast to the right, maybe we will want to accelerate in the vertical upwards direction, right? So x and y could be dependent on one another, not just through time. For example, let's assume that x prime is equal to x and y prime is equal to 2yt, right? So as you increase your values of x, the rate for which you change in that direction will increase. So what type of function satisfies that? So the derivative of something is equal to itself. What function could that be? So you're like, okay, well, I know that exponentials satisfy that property. So for example, e to the t will work, and also any constant multiples of that exponential function will also work. Also, if you think about this way for this particular function, the derivative of e to the t will be equal to e to the t, not 2e to the t. But if we think about this from a chain rule, the derivative of e to the 2t will be equal to 2e to the 2t, and also there could be some constant in front of there, so that will also work. So those are pretty easy, but what if we have both x and y inside the relations of x prime and y prime? So let's just take a look at that. So if we have that x prime of t is equal to 5x minus 2y squared, and y prime of t is equal to 2x plus 8y. And let's assume that we know where our particle is at time t is equal to 2. So let's assume when t is equal to 2, x is equal to 5, and when t is equal to 2, y is equal to 2. So with this bit of information, what is x of t and y of t equal to? Now, this problem is actually not that easy, generally speaking, for arbitrary functions of x, y for x, and arbitrary functions of x, y for y. So if you don't know how to find these values, we can always use approximations such as forward, backward, and central to approximate these values, right? So let's just bring back our forward difference approximations, because we can use these to our advantage. For example, let's look at dx dt, which we know is just going to be equal to the limit as epsilon x goes to 0 of f of x plus epsilon x minus f of x all over epsilon x, which is approximately equal to f of x plus epsilon x minus f of x over epsilon x. So we already know how x is changing with respect to time. It's changing like 5x minus 2y squared. And we already know what f is at 2, and we can inch into the future by any amount of time epsilon, provided that epsilon is approximately equal to 0, like 0.1, let's say. So let's assume we let epsilon x and epsilon y both be equal to 0.1, and if you have a computer, you can always make this a little bit more smaller to get more approximations. So what is x of 2 plus 1 equal to? So we know that x prime of 2 will be approximately equal to f of x of 2 plus our epsilon of 0.1 minus f of 2 all over 0.1. This is what we know. This was given to us to be equal to 5 because that's where x is at that particular point. And this is going to be our time step. So using this piece of information, we can say that this particular value, which is just going to be x of 2.1, will be approximately equal to x of 2 plus 0.1 times our function at the present point, which is just this f of 2. So keep in mind, f of xy is just going to be equal to 5x minus 2y squared, right? So if we go into the future at x plus h or y plus h or whatever you want to call it, we're just going to have, some time step evaluations for approximations. So before we actually jump into the numbers, let's actually write that out because that can get confusing, especially if this is new to you. So x of t plus some distance will be equal to, at least approximately, x of t plus some distance of x of 5 times x of t minus 2 times y of t, the quantity squared, and y of t plus epsilon y will be approximately equal to y of t plus epsilon y of 2 times x of t. We don't need a parentheses there, so 2 x of t plus 8 y of t. Right? So that's just us solving for or rewriting our derivative because this is what x prime is. So this thing right here, that's our x prime. And this thing right here, that's our y prime. And over here we have our x of t minus x of t over epsilon, y of t plus epsilon minus y of t over epsilon. And then we have our x prime, y prime in that bracketed term. So from here we can use our what we call initial conditions, x of 2 is equal to 5 and y of 2 is equal to 2, and just plug these in to approximate anywhere into the future, in particular 0.1 into the future of 2, which is going to be 2.1. Right, so once we have that, we're going to have that x of 2.1 will be approximately equal to x of 2, which is going to be equal to 5, plus 0.1 times 5 of x of 2, which is going to be equal to 5, minus 2y of 2 squared. And then for y of 2.1, we're going to have y of 2, which was given to be 2, plus our time step. And then we're going to have 2 times x of 2, which is given to be 5, and then plus 8 y of 2, which is given to be 2. And once you work out that math, you're going to have that's approximately equal to 6.7 and 4.6. So how do we interpret these particular numbers? So if we think about where we were at time t is equal to 2, so when t is equal to 2, our position xy was equal to 5 comma 2. So 1, 2, 3, 4, 5, 1, 2. So this is where we are at time t is equal to 2, and this is approximately where we are after 1 or 0.1 seconds, I guess you could say. So at, somewhere here and somewhere there. So that's an approximation for where we should be. I'm not going to put a green closed circle. That's sort of like an approximation of where we were. Who knows how we got there? But we're definitely approximately somewhere here. Because there's definitely some error with this because we're choosing 0.1 and 0.1 is definitely not 0. But there's definitely some path between t is equal to 2 and t is equal to 2.1 for which we have. And you should keep in mind that there is a little bit of error that sort of circles around that point that we have made in that approximation. Right, so that's pretty much just a quick outline of some of the things you should know when it comes to single variable calculus in the polar and parametric worlds. Definitely a lot more that we can discuss, but we'll work on it at a later time. Hope you enjoyed this video, and I'll see you in the next one. Take care.